I'm going to be talking to you about AWS Snapshots. I'm sure if you were playing a drinking game and you took a drink every time a cloud talk came up or AWS came up, you'd be feeling pretty good. Or if you didn't want to do adult beverages, you would have hit your water consumption for the day. But I've got really good news for you. I think a lot of you can relate to working with AWS Snapshots. It kind of goes back to more traditional disk forensics, and you're going to see through this that it just makes it really easy. So there's a lot of benefits to this. So a little bit about who I am. I'm a lead specialist at KPMG, and I help do a lot of our internal automation. We build a lot of internal tools. We use a lot of other tools. We create kind of orchestration flows for all of that for our different investigation workflows. I've started diving into the ML AI world a little bit, and I love it. I think Matt said it really good this morning. One, Matt's keynote was awesome, was it not? Yeah. But he said something that was kind of important, and that was like, ML and AI aren't buzzwords anymore. Like, it's here. And so right now, my thought process is, if I can utilize those tools as well as I learned how to utilize, Python or Rust or whatever other tool for building forensic parsers and orchestration stuff, like, where could I take that to? And I think that's kind of the next stage of my learning path here. And I think that's where we're all going to be headed. I would even make a bet to say, as much as we're hearing about cloud, even this year presentations, last year, there was a lot of it. I bet next year we're going to start seeing the AI ML stuff coming out a lot more. And so I'm really looking forward to that. On the weekends, I like to prospect. Who doesn't like to look for gold nuggets in the mountains? All right, so let's talk about scope real quick. I think if you listen to Jonathan's talk, you heard him say many times, oh, well, we could talk about this, but that would be 2 hours. Oh, we could talk about that, but that's like a whole day, right? Because there's no question, cloud is complex, right? And then not only is cloud complex, but then you start thinking like, okay, now I'm in Azure, now I'm in AWS, now I'm in Google, like, it's hard. But the scope of what we're going to be talking here about is going to be on EBS volume snapshots. And like I said earlier, this is your more traditional disk analysis. So I think you're going to relate a lot to this. What we're not talking about here is we're not talking about that volatile memory, right? We're not talking about the memory on the EC2 instance. And we're definitely not talking about cloud logs at this point. So pretty tight in scope. It's going to make it really easy for you. All right, so the first thing we need to establish is like, what is an EBS snapshot? So you have EBS volumes, and that's what you have connected to your EC2 instances, which is like your VMs, right? And so the snapshot is like a point in time backup. And this can be used for things like disaster recovery, mitigation, compliance, and of course now forensic investigations. So these snapshots are stored on your S3, and they're incremental backups. And this is kind of cool, because what that means is it's a lower storage cost for you. Remember, now that we're investigating in the cloud, we have to start thinking about costs associated with what we're doing, right? So things like incremental backups play a part on storage costs, and then you also have to think about bandwidth too. Bandwidth might come into play into cost as well. All right, so snapshots can be used to create new EBS volumes, and we're going to see that here in a second. And the best part is those can be shared with across different accounts. So now we want to start talking about like, what are the common analysis techniques we can use for these. No matter what, the first stage is we're going to have to create a snapshot. Okay, So then once we've created the snapshot, there's kind of two different methods that are highly used right now. The first one is that we can take that EBS volume, we can create a new EBS volume from that snapshot, and then we can attach that to our investigation machine, our EC2 instance. Okay, so the second big method that we're looking at here is we can download that snapshot and we can just work directly off of it as if it were an image. Okay, pretty easy. Again, going back to that traditional disk analysis, you're very familiar with that process at that point. All right, so obviously for method number one, it just goes, we got to talk about the automated forensic orchestrator. Big thank you. I know Jonathan has thrown out a lot of contribution into this document, and it's really good because it talks about how you automate that forensic workflow within AWS. So if we zoom in a little bit, this is kind of where it happens, where we've detected an alert for an EC2 instance, there's been malware, something happened, it's compromised. And so what we're gonna do is we're gonna look at step 9 in this whole methodology, specifically B, where we say, okay, let's create that snapshot, and then we're gonna share that snapshot with our forensic account, and we're gonna create a new volume from that snapshot, and then we're going to attach it to our EC2 instance. So that's where we do the investigation from. At this point, it's basically a mounted drive. So everything you do traditionally is gonna work here. So now let's talk a little bit about a second method. And this is where you just download the snapshot directly. And then you basically, at this point, you have a DD image, right? And then you can work off of that. So cold snap is kind of traditionally like one of the best ways you can do that. And what's really cool about this technique is now you're not having to restore your snapshot to a volume and then connect your volume to another EC2 instance. So it's a little bit easier to automate this pipeline. Here's a good tweet from Cowan talking about how fast he downloaded 160 gigabyte image. So 3 minutes, 48 seconds. It's pretty awesome. Because remember, traditionally, you've got to go out to the client site in a place you don't want to go. I don't know, it could be like Texas in the summer. And then now you've got to wait for hours and hours while you image this stuff, where now you just get it in 3 minutes. Pretty awesome, huh? But I need to stop here real quick because Cold Snap is written in Rust. And if I didn't throw in a Rust plug here, well, I want to be me. I love Rust, one of my favorite tools. I think the Aon people that came up here just now, I think, I was Seyer, is written in Rust and it's fast, right? So, people are starting to adapt this a little bit, and that's great because forensic tools are only going to get faster now. All right, so now we're going to kind of talk about this new method of doing things. But there's something we need to do first. We need to understand how to directly interact with our AWS snapshots. To know what we can do, we go down to the API documentation level and we see kind of a list of their APIs. What's cool is like that's not a lot. There's what, 6 APIs on there. Now there's really only about 4 of those that I want to talk about. The first one is going to be list snapshot blocks. So what this API is going to let you do is it's going to allow you to list all of the data blocks associated with this snapshot. And it's going to give you the index and the offset and then a token associated with that block. Because then we've got to use get snapshot block and pass it which block we want along with that token so that now we can access that data for it, okay? So then there's 2 other APIs I want to talk to you about, or just mention at least, and that's the list changed blocks. This is really cool because now what you can do is you can take a snapshot at one point in time and do a differential with a snapshot at a different point in time. We'll talk a little bit more about this in a minute, but like after this, Kevin's going to come up here and talk to you a little bit about file system differentials for quick wins. And so when you start thinking about that process of taking differentials to find stuff, like this could play a part in that, right? Except for at a large scale. The other one I want to talk about, put snapshot block, because, you know, forensics, we're just reading, but now you can actually write data to a snapshot and put it back in. I'm not a red teamer, but sometimes I like to think like, oh, I could do something cool like a red teamer maybe, I don't know. But this is one I would like to think about, because it's like, how cool would it be? How cool would it be? Someone would have a bad day. But like, if you already have access to their cloud environment and you were like, hey, I'm going to put this like malware back into a snapshot, then I'm going to restore the snapshot back to the volumes that are attached to all these EC2 instances. I don't know. Maybe you could do something cool with that. I don't know how it would work. Never researched it, but maybe someone should play with it. All right. So now that we know how to list the blocks in our snapshot, and then we know how to get the data for that block, like what's the next step here? And so what we can do is we can start layering on read and seek capabilities for this, okay? So you shouldn't have to worry about what REST request do I need to make to the API to get this data? How do I automate that? Let's obscure it within a library that allows us to create read and seek implementations. So if you were doing this in Python, because you can do all of this in Python, that's fine. Nothing against Python here. You would be basically essentially creating a file-like object in Python. And that's really cool because there are libraries that can handle that. So once you create that library and kind of obfuscate away those underlying like REST requests, this is kind of an example of some code where it's like, okay, now if I created a snapshot handle, I can just skip to certain offsets and then read from those offsets directly. And this is kind of really powerful because we can do stuff like this. Okay, granted, one, I need to apologize because this is going to look like a blinking Christmas tree. But what's cool about this is we can say, hey, read from a snapshot at this offset, this length of data. Okay, and in this example, great, there's a file there. And it works out because I knew exactly what offset I needed to go to and what length that this file existed for. But we need to do that dynamically. As great as this is, like, let's take it to the next step. So we start thinking about file system enumeration, okay? Because at this point, I can read a snapshot like it's just any other device. And now I want to start piping that through a file system enumeration layer, okay? TSK is great for this because with TSK, we can say things like, hey, I'm going to use my own object for reading from, and I can implement how it gets read and how I seek to different places. And so now I can just pass my snapshot handle that we were just looking at a minute ago into TSK, and all of a sudden, TSK will do everything for us, right? And that's really powerful because now we can stream a snapshot straight through a file system parsing library, right? Again, you could do this in Python, and if you did, you could even if you went this way too, you could create bindings for this. But imagine passing this to things like DFIRs, right? And so what's cool about this is like, maybe you're getting the idea like, whoa, like I could do this at scale and just like, you know, stream file systems from all my snapshots across an account. It's pretty cool. But then it's like, okay, now that I can enumerate the file system, what's next? That means we can get file objects now. We can iterate the file system, look for something we want, have like a handle open to any given file. So now we can pass that off to another library. And we can use whatever library we want as long as that library takes into account a file-like object. So in this case, we're looking at EVTX parser. This is a part of the Rust EVTX library. Zach was up here yesterday talking about Hayabusa, by far one of my all-time favorite tools. And the underlying library behind it is the Rust EVTX library. And I actually get to contribute to that library, which I'm really excited about because I added support for recovery of records, which is not something you normally see in other event log libraries. Not to mention, if you watched his talk, you saw how fast it is. It is the fastest library I've ever seen at handling this type, I say this type of data, event logs. Fantastic. All right, so now that we're using another library that can parse EVTX data, it takes in a file like object. We can do cool stuff. So I'm gonna show you a demo because you wouldn't believe me if I told you, but what if I showed you? All right, but before I do that, I need everybody to help me support this new term that maybe I coined, I hope I coined, but maybe someone used it. And that's minimal viable data because it allows for speedy analysis. So remember, Snapshot downloaded, or I'm sorry, Cold Snap downloaded the entire snapshot. What we're doing here is we're streaming only the data that we need to reconstruct the file system and then whatever data we want to read from. And that's it, nothing else. All right, so here's a little demo. I created a tool. It's called EVT Extractor. You're going to get a link to all of it and everything in a minute. And what we're going to do is we're going to extract out all of the EVTX files from a snapshot and then pass those files off to Chainsaw. And then we're going to aggregate the results of that for a better view of the data. If you saw Hayabusa yesterday, Chainsaw is very similar to Hayabusa. I actually prefer Hayabusa a little bit more because they have a easier syntax for creating detection rules, which I really like, and you can kind of use resource files. So like if you wanted to create a list of tools you want to look for, like you can just import those into your detections. It's really nice. So what we're seeing here is we just extracted out all of the EVTX files from our snapshot. We passed those to Chainsaw. Chainsaw used Sigma rules to look for detections within those event logs. And then we went ahead and aggregated those results. And here are all of the Sigma detections that we found within our snapshot. That's freaking amazing. Sorry, I get really excited at that. All right. So, and you also saw in the Hayabusa talk too, you know, you could have tens of thousands of hits, right? But when you start aggregating that data, like I can go through this, right? I might not be able to go through hundreds, maybe thousands of detections, but now I'm just looking at the aggregated view of, hey, what's even in this data set? What detections do I have? I can go from there. I didn't do it here, but just as easily, you could add in the criticality of it. So you could, you know, sort by critical, high, medium, low, informational, whatever. All right. So when you have the slide, I always like to throw up one of, hey, this is what the commands we're running. This is what each part of the command is doing. And it just makes it easier. I always, you know, I welcome everyone to go replicate this on your own. This is how you learn. And then I want to talk a little bit about this. So RIP forensic lunch. Well, not really, like we could bring it back maybe, but I do miss it. But I started making some dev videos. I call it deving in DFIR. And on one of them, I do this. I say, hey, let's run Hayabusa. Let's grab all of these detection alerts, and then let's start kind of mapping them out. This is using Neo4j. But you can use many other solutions out there to graph this type of data, right? So now it's like, imagine doing this at scale. Like imagine just being able to say, hey, I'm going to enumerate all of my EC2 instances in my Azure account. And then for each instance, I'm going to look at, you know, all the EBS volumes. I could create a snapshot, and then I could stream all of this stuff through said snapshots. And now I could easily just start doing hunting using this method. Kind of cool to think about, right? I do want to talk about the concept of a disk cache though, because remember that when you enumerate the file system, you're going from, maybe the front, logical offset 0 to the end of the disk, back to the middle. There's a lot of IO and you're jumping around a lot. So if you don't use any type of disk cache, what's going to happen is you're going to keep pinging the snapshot APIs, right? You're going to have to keep downloading the same blocks, and that's a little bit repetitive. So it's just going to be a lot faster implementing a disk cache. What's cool about this is the same thing that ColdSnap does. When you download an image with ColdSnap, it's going to create a sparse file. And so what that means is if there was space in a snapshot that wasn't used, you're not going to have any data for that. And it's one of those things where, like, if it wasn't used, why include it in your snapshot? And again, that plays into cost too. Like, now you're saving on both space and money. Great. What's really neat about that is because we're implementing this disk cache, you can open up that cache in something like FTK Imager and still explore it like it's a regular image, right? Because whatever data the file system library read, it got preserved into the disk cache, and it had enough to enumerate the file system, right? So that's pretty cool. And I got to kind of give a shout out real quick because this is something cool that happened on the forensic lunch. So the good doctor, Bradley Schatz, came on and was talking about his amazing product, Evimetry. And he was showing something, and I found this just mind-blowing. And it was so what you do is you connect your source device to his hardware, and that's what you're going to image, and you're writing it out to another, you're writing out the source image to an image, right? The source drive to an image. But you could share that as an iSCSI device, and then while you're creating an image, you can explore the file system and do stuff. And as you explore the file system and open files, it retains that data into the image as you do it. And that to me was just eye-opening, because I realized, like, once you control the reads, like, you can kind of do anything you want, right? So Cowan said it really good when he was kind of summarizing what he was doing up, and he said, as he's browsing this iSCSI shared device, each time he accesses something, he's actually retaining a copy of whatever he's accessing into the image itself. Just brilliant. But then it's like, okay, like, this is all really cool. Like, where else could we take this? I kind of, talked about the graphing. It would be really cool to create a tool that does that at scale. Obviously, I haven't done that. I think one of you should do that. Let me know how it goes. And I say next steps, aka what I'm dreaming of, because, like, at this point, I've got a 1-year-old and a 3-year-old. Like, I can hardly get anything done. So I would love it if someone just took this research and ran with it. I do think it would be really cool to implement a device driver on top of this, right? Because then you could just, like, stream in your snapshot and then browse it just like a normal file system. But there's a lot of power in that too, because at this point, you don't have to write your own tools to interact specifically with, this library. You could use any tool on it, and it's still going to do the same thing, because that tool's reading from a file natively, like a file system just sees it like normal, and then it's retaining that data into the snapshot or into the disk cache, and it's able to read all of that. So I think that would be really cool, because it's always good to be tool agnostic. And then finally, kind of like I mentioned earlier, a data diffing utility. I'm really excited to see Ken's next talk, because he's going to talk about what he's doing with file system differentials, being able to do differentials, especially against things like a base image or state, would be really powerful. And, now you can selectively do that at scale. Pretty cool. All right, so the big question is, where can I access this? I want to play around with it. Glad you asked. All right, so if you're using Rust, which I hope more and more of you start doing, it's on Crates.io. Crates.io is the PyPy for Rust, basically. And if you don't know something about Rust, it's that using other people's libraries is as easy as Python, even though you're writing on a low-level language like C. And that is mind-blowing. Literally, it's almost as easy as just importing something. That doesn't exist for things like C. Like, there's no concept of that. Now you can do stuff like that. Anyways, yeah, Rust is great. All right, so a little bit about where you can find these different projects. We talked about the AWS snapshot is called AWS Snap.io, but that's really only one small piece of it, right? And so you saw the EVTX extractor tool, and that's kind of its own project because there's still a third piece of that, and that's Rust bindings for libtsk. So what the actual extraction tool is doing is it's importing the AWS Snapshot.io library, and then it's layering the TSK bindings on top of it. And then it's doing the logic for, hey, I want you to iterate the NTFS file systems, and then I want you to iterate the Windows event log folder, and then just pull out the event logs like that. All right. Again, Chainsaw, I highly recommend it, but Hayabusa is my go-to for running Sigma rules against large EVTX data sets or just any EVTX data set. It just makes the whole process really easy. I think it's worth it to create some detections. You can share those integrated into your pipelines, fun stuff. And then a YouTube video if you want to see like how you can do graphing really easy, and then mix with detection rules, and being able to do that across kind of an enterprise is a lot of fun. So just fun stuff for you to explore. So thank you all for coming. I wanted to give another shout out to Cowan because he was the one that helped me get started with this. He came up with the idea of, hey, we should be able to use the library kind of like Cold Snap does, but because snapshots are incremental, we need to grab the first snapshot, layer on top a second snapshot, and then keep doing that to get to whatever level we want to get to. And within our testing, we actually found that that's not the case, that you can actually use the list blocks, and it's, I guess, in AWS's backend, it's actually going to give you the complete image for any snapshot at any given point, which made all of this so much easier. So at that point, we're like, hey, let's just implement read and seek based off of this, and then throw it into TSK or something else. So that's kind of how the project came about, and took it a little bit further. So I would love to see what other people do with it. You can find me on LinkedIn. There's my GitHub. I do have a Twitter, Forensic Matt on Twitter, but I've kind of taken a break, I guess, for right now. I don't know. We'll see what happens with X. So find me on LinkedIn. All right. And with that, we can jump into any questions. Questions?
Yep, back here.
Have you done any, I'm curious in terms of performance returns, if it only takes 3 minutes to download the entire DD image, you know, what's the payoff between, okay, I'm just going to take the 3 minutes to download the DD image and then do automated processing of however many images versus downloading or targeting the API and just pulling out specific files on the snapshot?
Yeah, I haven't actually benchmarked anything. Sounds like a great project for someone to do. I should, but I only have so much time. I just thought it was cool that you could do all this. Hopefully there's some time savings in it.
Yeah. So follow up to that. So you mentioned going at scale, right? So you could basically enumerate all EC2s in an account, all EBS volumes, all snapshots. And if you were looking just to pull EVTXs from those, that would probably scale a lot better using this method rather than downloading hundreds of gigabytes, even if it's fast, right? You still have to store it. Or in this case, you're just streaming the EVTXs down, if that makes sense. Is that kind of what you were thinking?
Yeah, I think going back to that minimal data, like we're just grabbing the data that we want to retain. Granted, at the end of the day, you have a disk cache, but you could clean that up, like because yeah, if you had a lot of snapshots to go through, you might want to keep disk usage to a minimum. So yeah, I think it would work pretty well.
Question at the back right. Question at the back right.
Right here. No, behind you. Just kidding. First of all, I remain impressed at like the ingenuity like that you constantly have in doing this sort of stuff, and obviously David on the back end. So major kudos to you. If your panhandling doesn't work out, you should check out cybersecurity. You might do well there. But so you explained having a disk cache, right? After reading all this sorts of stuff that you can go back and look at. Can you kind of expand a little bit more on what specifically you're reading live and how much of the disk as compared to downloading the entire disk, right? So there's enough of it that you're downloading, you have a cache, and you can explore it, right? So can you explain a little bit specifically what you're reading, and as that relates to your example there of how you extracted and parsed EBTX files, like how would you know where specifically to look on disk, and how are you reading and extracting this?
Yeah, so I think that would be another good metric to capture is like, do it again and compare like the actual data blocks that got downloaded against like the full one you would get from Cold Snap. But again, because we implemented read seek and then fed that to TSK is actually doing the file system enumeration. So I'm not 100% sure like on the like percentage metrics of like, hey, like out of the entire disk, how much is needed for file system enumeration. But basically at the end of the day, you're only going to cache what TSK needed to enumerate the file system, and then what TSK needed to read the data from the EBTX files. Granted, I will say, when you use the get snapshot or get block API for the EBS or the EBS API, they're in chunks. It's almost like, and it's much larger than your traditional like just like Windows cluster, right? So it's like a chunk of like 56 megabytes or something like that. So even though you might only need like, let's say like 2 clusters here, 2 clusters there, you're getting a lot more than 2 clusters back from the API. So that's getting cached. So the data blocks returned to you are much larger than probably what's required or needed by TSK. So there's that to account for as well. Does that answer your question? Sorry, I didn't hear that.
He has a lot more, so he'll talk to you after.
Oh, okay. Okay, cool. Well,
we have one more back here.
All right.
Sorry, just back another one with the disk cache. Sitting here in the dark. With the disk cache, once you've created that cache, so you're accessing it through TSK, are you then able to create a sparse image from the cache data that you then be able to preserve?
Yeah, I mean, it's already basically an image, right? Because it already wrote that data. It's basically a sparse DD file. Well, it's basically a DD file. It's just, sparse data from what you pulled back from the snapshot. But yeah, I mean, at that point, it is a DD image. And that's why FTK Imager can already enumerate it, is because it's just looking at it as a raw DD, and then it's enumerating the file system, and there's guaranteed to be enough data to enumerate that file system for you.
All right, thank you.
Awesome. Thank you, everyone.